So this is the dataset collection from University of Michigan. So this one particularly offers you the datasets in GML format. Just give me a minute. I'll share this link with you if you are interested in looking at some of the online datasets. So in addition to these datasets, you can see a few other websites here. So even the Stanford Large Network Dataset Collection is listed here. You have few other datasets here. So it will help if you go and explore. So some datasets might be redundant here and there. What I can actually do is download a file from here in the GML format. So if you look at here, this Karate network, so it is given to you in the GML format here. So either I can just load it to you and show. Rather, let's do what the graph which we were having. Let's write it down in a GML format and then read it. So the two formats which we are just going to see now are GML and GraphML, and they are quite often used. So both of these formats, I'll once store a file and then show you how it looks like. So the advantage it has is it also stores the attributes. Let me just add a few more attributes for the sake of completion. So let me say I'm also adding an LName attribute. How many nodes will we having in the graph? Let me see. You can also use something called g.vcount to look at the number of nodes in a graph, or you can look at the length of g.vs. I'm giving them some last name. And let me just take 3 like this. So I have two attributes associated with the nodes now and one attribute associated with the edges in this particular graph G. I'm going to write it down in a GML file. And let me name it G underscore gml.csv. And let's look at this file here. So this file has a format something like this. So this one tells you that it is a directed graph. Then every node has an entry here with its ID, its F name, and its L name. So if I had more attributes, they'll also be listed here. So every node with its attributes is listed here. And then you have edges here. And again, every edge has three things: a source, a target, and a weight. This is how your graph is stored in the GML format, and again you can read it back from the GML format, and unlike in the other cases, when you read it back from the GML format, attributes will go to their right places. So if I do something,
Please share your screen.
oops, I'm very sorry, I just forgot it. It's visible now, right?
Yes, ma'am.
Okay, let me do all over it again. You should have told me previously. Okay, so this was the data set I wanted to show you. This is from the University of Michigan, and all these data sets, they are in the GML format here. So you can go download any one file and do that. So I've actually downloaded this file here, and when you open it, you can see a karate.gml file here. Let me just open it and show it to you. So this is how a GML format looks like. So you have graph, so every node with an ID. So you can see each node with its ID here. and every edge has two things associated with it. One is a source and other is a target. So in this particular case, I do not have any vertex or edge attributes in this particular file. So what we'll do is, for our own network which we have created, we'll look at how nodes and edge attributes are stored in the GML format. So what I have done here is, I have associated one more attribute with all of our vertices, which is lname. Passed it a list here. Then what I have done is, I have written this graph in this file g underscore gml.csv. So let's look at this file now. So this is how this file appears to be. So you can see here now, every graph it has, so the graph is directed, and for every node you have three things. One is ID, one is fname, and another is lname. So these are different nodes stored with their attributes, and then this is for the edges. You have for every edge a source, the target. So for every UV pair, this is UV, and then a weight associated with every edge. So this is how a GML format looks like. And then we read this graph back. So we are reading this graph back from our GML file. Our file name was g underscore gml.csv. And now if you look at the summary of this graph here, you can see that it's a directed graph, a weighted graph. Vertices are not named, that is, I do not have any attribute name here. So the attributes have gone to their correct places. So I have an F name and L name for each vertex. Each vertex also has an ID here, and then the weight. Every edge has a weight here. So this was one format. Another commonly used format is GraphML. So GML is graph modeling language and GML is graph markup language. So let us just store a graph in this format and let's see how does it differ from our GML format. So I'm going to write this in the GraphML format here. So when you write it in the GraphML format, I have this file. So it's a file which has various tabs. So it's actually an XML format. So quite complicated as compared to the GML one, but you can still see that every attribute for every node is stored here. So one advantage of storing the graphs in GraphML format is, so you can use the GML format because it looks simpler. GraphML format you can use when the graphs you have are nested. What I mean by nested graphs are, so let's say you have a node attribute, and let's say the attribute value is not a string, it is another graph. So if somehow you have a node inside a node or a graph inside a graph, then the GraphML format suits best because it has a nested structure as in XML. Furthermore, if you have hypergraphs, does anyone know what hypergraphs are? So generally, if we look at graphs, each edge connects two endpoints. So we always have a UV pair. We never have a UVW pair. So hypergraphs are where one edge can connect more than one vertex. So one edge can be connecting four vertices, five vertices, three vertices. So those kind of graphs are called hypergraphs. So if you have those kind of data structures, then you can use this GraphML format here. And again, you can read back from this GraphML using a similar function. And it also, I've got an error here, just a second. Okay, it says that my graph ML support is disabled here. I'll look into it and get back to you why this one is not working here. If you are trying it along with me, can anyone let me know if it's running on your system? Okay, and then I'll let you know why it's not working here. So this one also you can use it to load and store your graphs. So there are certain other formats as we were discussing. The other one was this pickled graph or a .NET format. So pickled graph you can use them when you have very big networks. For very large network, this pickle format is generally suitable. And then as I told you that sometimes none of these formats help. The graphs you have stored, they are in some weird format. So you have to import them as a pandas data frame and then you can quickly do some operations to work with them. So as an example, let's look at a retweet network here. Sorry. So this website, it gives me a large number of networks. Let me again show you here, explore. This repository here. So it has again a lot of different networks, different kind of networks, categorized networks. So I'm going to pick one retweet network from here. So actually among all these networks, I had figured out one network which was quite small. So this one over here, RT underscore retweet, this one has 96 vertices and 117 edges. So right now we can work with it. It's a small one. So here I have this file. This is rt-retweet.mtx. So it's altogether a different format, but it is nothing. It's called a matrix format. So we didn't see any functionality for matrix format as such in iGraph. So what it is, it just tells you that it's a matrix matrix coordinate pattern. This tells you that this matrix is actually symmetric. It tells you in this symmetric matrix there are 96 rows, 96 columns, and there are 117 entries. And this one tells you the rows and columns for 117 entries. So in a sense, what this has is nothing but an edge list only. Uh, but the edge list starts from this third line onwards. So let's just import this data into a pandas data frame and then see how I can make a network out of it. I am just going to save this file. It's my desktop. So this one over here. I'm just trying to look at what is its extension. So although it's said a txt while saving, if you look at the extension of this file, the extension is .mtx. Okay. Oh. So first of all, I'm going to import this file as a pandas data frame. So first I need to import pandas. And then I'm going to read this in a data frame. So let me name this data frame as edge list. I'm going to call the pd.readcsv function followed by the path of the file. See if I can copy from here. And my file name is rt-retweet.mtx. And I need to see if I have any separator in that file, need to take care of that. So my separator is nothing but a space here. Let's see what it takes it by default. What is the separator? So after doing this, I'm just going to see how this data frame looks like. So as of now, it has everything in just 2 lines. So my separator was a space here. So when I give my separator, you can see that this is how my data frame looks like. So since my first line, it was having 5 spaces, it divides that. So I could have actually used a header equals to none here. But that's okay, because anyhow I do not need this first line. In case this first line was also having some entries, so I didn't want it as a header, it should be data. In that case, you can pass another argument, header equals to none here. So now what I need to do with this data frame here, I need only these 2 entries, that too starting from the first row. So I need to extract this part of the data frame here. So I'm going to remove some columns from here. I need only the zeros and the first column here. I don't need columns 2, 3, 4, and 5. So I'm going to remove them. We have the command here, el.drop, and the column numbers which you want to drop here. And I want to drop 2, 3, 4, and 5. I'm going to set in place equals to true because I want to make changes to this data frame only. So I'm not returning anything here. And again, if I look at the value of EL, you can see that I only have my 2 columns now. And again, I want only the first, I want to delete this first row from here. So let's do that quickly. So there are various ways to do this. So one thing while programming, what helps is if you want to do a certain thing. Let's say I want to remove some columns or remove some rows. Then instead of going by the first principles and learning everything, you can just type it on Google, get the exact commands, and run them here. So now you can see this. Now my data frame seems perfect. It has 2 columns. So my source node and my target node. Now one more thing here. Assume that you were using this data for modeling information diffusion. Since it's a retweet network, it tells me who is tweeting to who is tweeting whose information actually. So here what it tells me is 6 is uh, tweeting a tweet which was posted by 1, or 8 is retweeting a post from 1. Again, 54 is retweeting a post from 1. So for 6 to retweet a post from 1, 6 should be a follower of 1. So I can say that this first column over here is a follower and the second one tells me a followee. So although it will not give me the complete followee pictures, but according to this much of tweet data based on who is retweeting from whom, I can figure out who is a follower and who is a followee. So I'm going to rename both of these columns to follower and followee. Next, now what I can do is I can create a graph from it, but there will be one problem in that graph. This graph is going to be directed, but I do not want an edge from 6 to 1. I want an edge from 1 to 6, because if I look at the direction of information diffusion, information goes from followee to follower, not from the follower to followee. So while making a graph out of it, I would want to swap both of these columns so that my edge goes from 1 to 6, 1 to 8, so on and so forth. So before doing that, what I'm going to do is I'm going to re-index my data frame. So that I'm going to swap both of these columns over here. So I'm going to re-index it according to the way that my columns should be followee and then follower. Now if you look at EL, You have a followee and then a follower. I did some mistake here. Just give me a moment. Need to do this all over. So this one is a followee here. So now I get a followee and a follower here. Now I want to create a graph out of this data frame. So what I'm going to do is I'm going to convert all these into tuples. So once I have tuples, I can directly pass those tuples into my create graph function. So I'll just do it and we'll understand what's happening here. I'm going to convert all these rows into tuples. So these are my tuples. So I've done nothing, but everything came in the form of a tuple. Now I can pass these tuples maybe to my g.add_edges function. Rather, I have one more function if you have a list of tuples like this. So let me say that it's a retweet network. We have a function here which creates a graph from a list of tuples, which is called a tuple list function. I'm going to pass these tuples to this function, and since this graph is directed equals to tree. My graph is formed. Now we'll observe what problem happens here with iGraph. So if you look at all these vertices which we have added to the graph, so unlike in the case of Facebook, the index doesn't start from 0. And I'm not sure whether there are certain vertices missing in between or not. So you know my original file also, and let's look at the edge list of this graph. So the edge list of the graph looks something like this: 0, 1, 0, 2, 0, 3, 0, 4, so on and so forth. But the tuples we passed to it were 1, 6, 1, 8, 154. But I don't see anything like that here when I look at the edges of this graph. So what actually happened is, the reason is all these nodes, they have been re-indexed. So I don't know what became 0 here. So something from here has got an index 0 in my graph. Some vertex from here has got an index 1 in my graph, so on and so forth. So for that, and it can also happen when you import a data set not from a GML format, but maybe from an adjacency list or edge list. So you can see such kinds of things, that the edges which will appear here will be different. So in that case, let me look at the brief summary of this graph. So if you look at the summary of this graph here, so it's a directed graph and it becomes a named graph here, and every vertex has a name here. So what is that name? That name is actually, what is its value here? So vertex 0, let me actually show this name to you. So if we look at these names here, you can see. So what has happened is, vertex 0 has a name 1 here, vertex 1 has a name 6, vertex 2 has a name 8. So you know that mapping from here. So what happened is, whatever was this 1 here became a 0 here. Whatever was a 6 here has become the node index 1 here, so on and so forth. So it tells you which node index is mapping to which name. So this way you can work out with your original data as well, in case something has been relabeled here. If you want to look at the exact mapping, you can create a dictionary out of this. So what I'm going to show you here is a vertex name, a dictionary, such that we can see an exact dictionary here. So 1 is mapped to 0, So these are the first column here are the names from the original file or the triples, and the second one are the indices in my current I graph. So 1 has been mapped to 0, 6 has been mapped to 1, 8 has been mapped to 2, so on and so forth. So you need to take care of these labeling. So sometimes, let's say you stored a graph and then you opened it in iGraph, then these labels might have changed. So you need to look at these attributes. So sometimes this attribute is named, sometimes this attribute is also labeled depending on from where you have imported this graph. You can quickly visualize this weak network. And this is how this network looks like. Okay, so we are done with the creation of the basic graphs, loading and storing of the graphs. So previously we have looked at some deterministic graph generators, so which can create a graph which is like a star or a tree or a ring. What we are going to do now is look at some randomized graph generators and how they are actually useful. So whenever we talk about real world data, let's say you are talking about modeling Facebook or Twitter or some other protein interaction network or the network of web pages on internet, those networks, they do not look like a tree or a ring or a Peterson graph or any of those graphs you studied in a basic graph theory course. Those graphs are the real world networks and they look like something totally different. So for generating those kind of graphs, we actually use these random graph generators, which are based on certain principles, which we'll discuss one by one now. But before that, I would want all of you to watch a quick video so that we get the right motivation set up for this. I'm going to share the link of this video here. So go ahead, watch this video. Once you are done watching the video, please type a +1 in the chat window, and you can also succeed that +1 with anything if you have to say about this video. Okay, so I think except me, everyone has watched it. Okay, so Chetan says this video gives us an idea that all people on an average are six or fewer social connections away from each other. Can someone guess what this number is for Facebook? So although he mentioned that it is 5 or even 4, so you can actually calculate this number for every network by figuring out what is its average path length. So you calculate a path length between every two possible nodes and you take an average of that, and this value turns out to be 3.5 for Facebook. Anyways, so what this video is trying to help us understand is how do you start modeling real world networks. And the very first kind of models that were used were the random networks. So as explained in the video, you have certain nodes in the graph and then you randomly place an edge between any two nodes. We are going to implement that first model over here, and we already know what are the drawbacks of random models, but they are good in the sense that obtaining bounds on these networks are very easy. So it's easy to study the random networks theoretically as compared to other networks. So I'm going to build a random network here. So you have an inbuilt function which is named after the two scientists who came up with this model, Eldros and Bain. Sorry. So your first argument is the number of nodes, and second argument is the probability. So that's why we call these models the stochastic models or the random network generators. As we'll see, every time you run this code, it will give you a different graph. Let me rather take just 10 nodes for now. So on 10 nodes, we can have 10 choose two edges, I think, which is what 45. So what happens is each of these edge has a probability of zero point 0.2 of showing up. If I make it zero point 0.5, it's like you are flipping a coin for each of these 45 edges. If you get a head, that edge is in the graph. If you get a tail, that edge is not in the graph. So you can change this probability. And for now, I'm going to make it an undirected graph. Hmm. So here I have this graph. Let's load in seed. Let me plot it here itself. I want to make it smaller. To check what exactly to do for this, I want to. Okay, better. What I can do is I can save this plot. So here is the graph which is generated. So here some vertices are cut. So if I increase the margin, it will fit right in this box here. So you can look at this graph, and then when I generate it a second time, you will see that the graph has actually changed, which won't happen in the case of your deterministic generators. So we have already seen what is the problem with these random graphs. So to summarize, these real world networks, they have two properties which are very interesting. So the first is that they have a small average path length, as we learned from 6 degrees of separation. So we can say that their average path length or diameter is low. And second, they have a high clustering. So the problem with these adversarial networks is they have a lower diameter. Their average path length is also low, but they don't have a very high value of clustering. That clustering is small there. Basically, a friend of a friend is not my friend. Anybody can be a friend with anybody else in this network, but that's not how generally it happens in the real world. So most of the times we are organized in some clusters and communities. So edges are, you'll see dense edges in a particular place. They are not dispersed randomly everywhere. So what we do for that is, let me just give me a minute. So if you look at this picture over here, he has actually illustrated it in the video also. If you look at this picture here, so this one is a random graph. So I have just arranged it in a circular fashion. You can actually do that here also. So what I can just do is I can change its layout. I need to write it here. And look at this graph, you get it in a circular fashion over here. So this is my random graph. So this one has a low diameter but also a low clustering. This one over here is a lattice or a regular graph where everyone is connected to two other people. So we call it a lattice or a regular graph where everyone has the same degree. So this one over here is a high value of clustering, unlike the random graph. But the problem here is it doesn't have a low diameter or a low average path length. So this one here will have a diameter of about n by 4 because you can jump 2 every time. So these two nodes will be the farthest in this network. So what was suggested is you create a mixture of both of these models. So you are actually going to use this model only, but you rewire some of its edges to get a network which is like this, which is a small world network. So let's try to do that here. We have already seen the limitations of the random network. So first I'm going to show you a lattice. The function I'm going to use here is the same function which is used to create this small world network over here. So here we have certain parameters. So the first one is dimension. So let me keep the dimension as 1 for now. Size tells me the number of nodes in every dimension. So let's have just 10 nodes as of now. Then we have next parameter which is called NEI. So NEI means to how many neighbors you want every node to connect to. So let me keep it 1 for now. So I want every node to be connected to just one neighbor on each side. P is the probability of rewiring. So if I keep P to be equal to 0, there is no rewiring. So if you see here, if you don't do any rewiring here, I keep this P 0. So you are actually going to get a lattice here. When I change the value of P and rewire it, I get something like a small world. And if I make this P equals to 1, it becomes a random network. So I'm keeping this P to be equal to 0 here. That's it. And then let me just look at this lattice here. So if you look at it here, it's a simple ring-like network. Let me also save it. I need to see what exactly we need to do to reduce the size of this box here. let me use no layout as of now. So I created a file here named lattice.png. So this is what you get if you don't do any rewiring, and every node is connected to one node on the left and one node on the right. Now what happens if I make this here as true? It means that every node should be connected to two nodes on the left and two nodes on the right. So let me just write it down here. The first argument is the dimension. Second argument is the number of nodes in each dimension. Third argument is the number of neighbors, how many nodes on the left and right you want to connect to. And fourth one is the probability of rewiring. So I now connected every node to two nodes on the left and two nodes on the right. And what you see is something like this. So every node is connected to two on the left and two on the right. So this is a lattice. If you want to convert it into a small wall network, you will need to change the value of this probability here. So I'm going to do some rewiring here. Rewiring probability is 0.2 for every edge. And when you do that, you see something like this. You see that some edges have been rewired here and there. If you keep this probability equal to 1, you will get a random network here. Next, let me make this as true. So I'm doing it in 2 dimensions. Let me have just 6 nodes in each dimension. For now, let's say every node is connected to one on the left and one on the right with 0 probability. So it's going to be a lattice in 2 dimensions. So it doesn't look very nice. So I can't see any pattern in here. So let me again change its layout. I'm going to use a grid layout here, which will arrange the nodes in nicely in a 2-dimensional grid. So when I do that, look at this lattice back and now you see a nice figure. You can see that every node is connected to one node on the left, right, top and bottom. And what happens if you make this value to be equal to 2? So every node should be connected to 2 on top, bottom, left and right. And you get something like this. And if you want to convert this lattice again into a small world network, you can do some sort of a rewiring here. And after rewiring, you get something like this. So some of the edges are rewired. So these are 2 very popular models which are used for graph generation. And again, they will give you a different graph every time you do them. Every time you generate these. So if you are working and trying to get some result with the help of these networks, you better generate a large number of networks and then report the average and standard deviation of the values rather than doing it just once and reporting the value. Now we have a third kind of a network here which was not discussed in that video. So there was an issue with the random graphs, therefore we came to the small world networks. So whenever you are trying to create a network which looks like a real world network, the way you do it generally is to look at certain properties of the real world network and then to ensure that these properties are present in your synthetic networks. So like we just saw, our real world networks have a small average path length. So we did that with the help of randomness. And then we saw that our real world networks have a higher clustering. So we took the help of a lattice-like structure, which helps us cluster nodes. But there is one thing which is missing in both of these, and that is actually degree distribution. Degree distribution is if I keep the degree of every node on the x-axis, and on the y-axis you plot how many nodes have that particular degree. So let me actually show you figure for degree distribution here. So this is done actually on a logarithmic scale here. So this is also an example of a degree distribution. So here on the x-axis you have the degrees of the nodes. So in this case you can see that, just a second. In this case, you can see that the degrees of the nodes, they go from 5 to 40. This is the random network which they have generated. This one seems to have generated from network X. And on the y-axis, you have the probability or the fraction of nodes having that degree. You can also write the absolute numbers. So this one is showing you the degree distribution for a random graph, which is bell-like distribution. So you can see that almost 8% of the nodes have this degree, then 7% of the nodes have this degree, so on and so forth. So the degree distribution for a random network is like this. If you look at the degree distribution for a scale-free network, can you guess how will it look like? So the curve for the degree distribution of a scale-free network. So if we do it for a lattice, every node has the same degree. It's going to be just 1 point on this in this figure here. So all the nodes have a same degree. But if you do some rewiring, still the degrees of all the nodes will almost be the same with some randomness here and there. But that's not how the degree distribution in the real world looks like. The degree distribution in the real world network looks something like this. So this figure here shows a clear difference between the two. So this one is how it looks like a random network. This is how it looks like a real world network. So this research was conducted around in the year 1990 by two scientists, Barabasi and his PhD student Reka Albert. So they took a large number of real world networks and looked at their degree distribution, and it was very different from what you see for a random network or for a scale-free network. So we have another method. So I'm not going into the details for creating a network whose degree distribution is like this. And this model is the most frequently model for your real world network. So most of the times, whenever you are using some synthetic networks to derive your results, you use this model. So this one is known as the Barabasi-Albert model. One difference it has from both the models is this. So both your random networks and lattice, they are non-evolutionary networks. That is, you can put all the nodes and you can mess around with the edges. On the other hand, Barabasi-Albert model is an evolutionary model. It evolves with time. So at time one, your network will be something. At time two, some new nodes will come and make certain connections. Time three, some other nodes will come and make certain connections. So in this function, this 10 is the number of nodes in the network, and 2 here tells me the number of connections each incoming node makes. So it's like a classroom in which initially only 5 students are sitting. Then the 6th one comes and makes some links. 7th one comes, makes some links. So this second parameter here is that number of links. And then you can see this network over here. So it doesn't have any kind of a organized structure. So you see that organization only when you look at the degree distribution of this network. So I'll talk more about degree distribution probably tomorrow. So here we looked at a few graph generators which which are random graph generators and generate the networks more similar to your real world networks. Now I'm moving to a slightly more interesting part in the terms that, so these networks which till now we are looking over here doesn't look very nice. So let us try to play around with the names of the vertices, their labels, their colors, so on and so forth. So this one is pretty straightforward. I can just pass certain parameters to this ig.plot function. So you can search for more parameters in the documentation. I'm going to show you some here. So the network I'm going to use here is again D, which was the network which we made at the beginning of the session, the network between some people. I can give a label to each of the vertices and let this label be the first name of each of these vertices here. Then I'm bounding it by a box. I hope this time it works well. Setting some margin here. So margin is so that your figures are saved properly. Like you were seeing in my figures, some of them were getting cut down. I can set the size of each vertex. So here I'm setting the size to be 30. So it's going to be 30 for each vertex. You can also have a different size for different vertices. In that case, you can pass a list here. So if I have 9 vertices, I can pass a list here having 9 values. So vertices will pick their sizes from there. So I'm having equal size for every vertex here. Then I have edge width. Again, I can pass the same edge width for every edge. or I can pass it a list actually having the weights of those edges. Then most of the times the edges which we are seeing in these figures are straight. Let's say I want a slightly curved edge so that my network looks nice. So I can use a curved attribute here, giving it a value of zero point 0.3. So 0 means perfectly straight lines, 1 means perfectly curvy lines. So took something in the middle. And then I can take a vertex color. Let's say I want black colored vertices. Then I have a label at every vertex, but we know that those labels are quite big. They might not fit in the vertex. So we have one attribute by which we can shift those labels up down. I'm going to set a distance from the label. So all the distances are going to, all the labels are going to be one distance away from my vertices. I can give a separate color to the boundaries of these vertices. So that's called vertex frame color. I'm taking red frame color for the vertices. I can also set the width of this boundary, and let me set the width of this boundary to be 5. Okay, got the error here. Let me see. Now this graph G which we want to plot. Vertex level, margin, vertex size. Not sure exactly at exactly which point it's giving an error. Let me cut it down to figure out where exactly we are having an error. This one works. Okay, let me try to do it one by one. This one is also working. I changes my vertex size to 30. So vertex size is also working. Oh, edge width. It changes my edge width also. After edge width, I'm trying to curve these edges. Yeah, so here it's giving me an error. Okay, I actually use edge dot curved. So this notation actually works in iGraph R. So it shows me my edges to be curved, and let me just paste that back here. Can someone try me help me to figure out the error? There is some small formatting error. It doesn't tell me exactly at which place it found an error. Okay, here I have an extra camera. So you see this graph here. So you will see all the labels at a particular distance from the vertices. The edges will be curved and the frame colors, frame widths and stuff. So this was if you want to visualize this graph in a different way. Now assume that I have certain attributes associated with the nodes and I want to make the node colors dependent on that attribute, which you might want in some kind of graphs. So as an example, assume that you are creating a network in which every person is a node and you have an attribute called BMI for every vertex. There has been a research done on this, and in this network, let's say you want to represent the people who are underweight with a blue color and the people who are overweight with a yellow color. So your colors are dependent on the attributes of the node. So how can you do that? So for that, I'm going to take a new attribute called gender associated with each vertex here, and then we'll see how we can change the colors based on the gender here. I'm going to give two values to this gender. So a person can either be a female and a male. I'm just taking some random values here. I have 9 nodes. Nine values here. So I've allocated gender to each of my vertices. Next, what I'm going to do is I'm going to take a color dictionary here. What my color dictionary will do, I have a dictionary which maps a gender to a color. So if the key in this dictionary is F, if it is a female, then corresponding to female, it has a pink color, and corresponding to male here, let's give it a blue color. Next, what I'm going to do is I'm going to give a color attribute to each of the node, and what this color attribute should be, this color attribute should be pink if the value here is a female and blue if the value in this list is a male. So what I'm going to do, so first of all, it is a list and this list takes its value from this dictionary, color dictionary. I'm going to iterate it over gender or G for G in G dot bs gender. So what I'm doing here is I have taken an iterator G which iterates over all of these values and I get a color dict of G. So color dict of F if this value is F, color dict of M if this value is M. I can also see the value of G dot vs color here. So I get all these colors here in my list. Now this attribute G dot vs color is directly read by your plot function. So if I call this plot function back, so I can do two things here. So either I can do vertex underscore color is my G dot vs color. This will work. Even if I don't give this any value, it will work. So if I execute this, you get this over here, blue nodes and pink nodes for males and females. Even if you remove this line here, even if you remove this parameter here, it will still work. So these attributes, so certain attributes are implicitly read. So color is one of them, shape is another, which we'll look for the bipartite networks. So this was about the edges. Same thing we can, sorry, this was about the nodes. Same thing we can do with edges also. So we have how many edges with us? We have 6 edges with us. So we can again associate an attribute with each of the edges. So let's say each of these people, they can be friends with each other or enemies with each other. Let me give it so we have looked at signed networks when we were looking at the data set. So let me take an attribute sign here. So the sign is plus for friendship and minus for enemy ship. So let's take more friendships and give some positivity. I have allocated the signs to my edges, and then again you can do the same thing. I can make a color dictionary for edges. If if it's positive edge, then let's give it a green color. And if it's a negative edge, let's give it a red color. And then we can do again the similar thing here. I'm assigning these colors based on this dictionary. So these are the colors for my edges. So G.es color. The name of the dictionary is ecolor dict. And since it is signed, let me use S for SIN as iterates over G.es sign. Now if you again plot this network over here, so let me remove the edge colors which were implicitly there. Did we have, so we didn't use any edge color here it seems. So now you can see that there are certain edges which will come in red color and others will come in green color. So green are the friendship ties, red are the enemyship ties. Then the next thing which we can work is the work with are the different network layouts. We have seen two layouts till now. I have shown you a circle layout and a grid layout. There are many more. So here I haven't used any particular layout. So it uses an automatic layout. Let's look at some layouts here. So here you can find out some of the layouts which are available. So what I'm going to do is so it's better to try these layouts on bigger networks instead of these smaller networks. So let's take our Facebook network, which was a big one having 4,000 nodes, and try to lay it out in different ways. So the name of my network was G underscore FB, is it? So this is the graph I'm having. I want to plot it with different layouts. I'm going to use an ig.plot. So no colors, nothing here. We are simply looking for the layouts. I can slightly play with vertex size. Let me make it small. This one will take some time over here. So this code is still executing. It will show up in a while. So as of now, I'm just using an automatic plotting of this Facebook graph. So it's difficult to visualize big networks because they take some time. So this one appears over here and you can't see much things here. So let me try with different layouts here. Let's say, let me try with a circle layout. So this one looks again very weird here. So what you can do is in this layout argument over here, you can pass these different things. So if you type it circle, it will give you a circular layout. This DRL is a distributed recursive layout. It is based on simulated annealing algorithm. Then you have certain layouts like this Switzerman, Ringgold, and all these over here, LGL. So these kind of layouts, they are based on force directed algorithms, as you can see here. So force directed algorithms, they try to visualize your network in a visually appealing way. And what they try to do is keep the edge intersection as low as possible. So whenever trying to figure out which layout suits the best for your network, you can always try with some layouts and then see which one looks good. Since it is taking some time to create these networks and look at them, I'll show you some layouts here for this Facebook network over here. So this is how this network looks like if you don't use any layout at all. I have slightly modified the vertex sizes and frame colors. So let's say when we try to draw it in a circular layout, it looks something like this and nothing is visible at all. This LGL format over here still looks better than the other ones, and you can see some clusters here. This is KK. So the best layout which works is, so this one is also not very good. Distributed recursive layout. So what works best for this kind of networks is what I personally think is this Fletcher-Ringgold algorithm. So you can always use an FR here and visualize your network. One thing, so this iGraph is also available in R, and you can either find all the better visualization there. So that has an interactive layout which is called TK plot. So it opens your graph in a new window. So here I can't do anything with my nodes and edges. There you can actually drag your nodes to different positions and do a lot of stuff with that graph once it comes to you. Similar to Jeffy, but can work with bigger networks over there. So these are different network layouts which you can use for visualization. We have 10 minutes left. So we'll do just a small thing here. So how do we deal with bipartite networks was a question. How do we represent bipartite graph? So unfortunately, there is no specific format in which you can show that a network is bipartite and store it. So you can, once you have generated a bipartite network, you can store it as a GML network. But if you are going to read any data set, it might not be that convenient. So let's try to take an online network data set, a small one for a bipartite network. So this one is a network data set. So this network is a bipartite network for 18 women and 14 informal social events. So what this tells you is which women attended which event. You're always going to see a tie from a woman to an event, never between two women and never between two events. Where I can get this data set. This one is not working out. Let me try finding this on a different website. So many times when they have some online data sets, they also show some basic statistics of those networks like degree distribution, cumulative distribution, K-core distribution, triangle distribution, number of closed triangles, so on and so forth. I just wanted a simple file for this. Just give me a moment. I'm trying to figure it out. This is the same link, but I'm unable to fetch the file from here. Let me see. I'll give you the link. Let me see if I already have this network downloaded with me. So I have this network with me here in this notepad file. I'll find the exact link and maybe send it to you. So this is a bipartite network and you get it something like this. So it's again an edge list kind of a format. So the first column here is women. So we have 18 women, and the second column here is an event. Now the question is, can we read this edge list directly? Do you think it will work? So I want this is a bipartite network. This is women one, this is club one or event one. This is women one, this is event two. So if I directly use that function of read edge list, what do you think will be the problem with that? If you read this particular network in any of whether be it network X or igraph R, you will run into problems because what is happening is this one and this one are different. But in your network which will be created, it will create a self loop from one to one. But we need to differentiate between the nodes which are there in the first column and the nodes which are there in the second column. So again, we need to do some data frame based operations here so that we can distinguish between the women and the clubs. I'm going to do that here. I'm going to import this CSV file. Just take the copy paste the code from here. So let me name it as TF here. So if you look at this file club here, again, you have to be careful about the format. So the format of this file is .edges. So sometimes you will find .mtx, sometimes you will find .edges, sometimes it will be a CSV, sometimes txt. So this is my data frame and somehow it ended up taking 3 columns. So I need to drop that last column there and I can use the same logic which I used here for dropping the column. I'm going to drop this column number 2. So I got this, but again here I have a problem. If you see here, the header is the problem. My first row was counted as the header. So I don't have a header in this file. I'm going to do a header equals to none here. So it has numbered my column names as 0, 1 and 2. So here I have my 0th column and my first column. But what is happening? My 0th column is for the women and my first column is for the clubs. So now we have to see here what we can do to actually tell to our program that it is a bipartite network and he should treat both of these columns in different ways. So I think there are only 5 minutes left. So we'll start it afresh in the tomorrow's session and then proceed with the information diffusion based hands-on. So I'm done. If you have any doubts, you can ask me.
Yes, participants. So if you have any query from ma'am, you may please ask before we take a lunch break. So yeah, Yatiman, the session was really very wonderful. But in the FDP, as we have done most of the things with the Network X, so it's the first session that we people have started with iGraph. So it will be very helpful for us if you can guide the participants with some resources to explore this library, because I found that when we explore the manual, so as it is very abstract way, it is given with a partial you can say usage of that function. So sometimes we held up with actual understanding of how to implement it. So if some good sites or some resources are there, so that from scratch, if somebody is learning this visualization part, so they can do easily.
Sure, ma'am. I'll do that.
Okay, ma'am. Fine, participants. So as soon as I will receive the corresponding material from ma'am, so I will upload the same for your reference. So see you all at 2:30 for the next session. So I request all of you to please fill up the attendance for this session. Thank you, Yati ma'am.
Thank you so much, ma'am.
So ma'am, the link will be same for tomorrow also.